Wait, what's this? Ah, the soul one.
I think I should put myself together and letting time by. If I lose this,
But there's so much to do. We have to do overlaps and electrical engineering. We have to do all this from
actually, I haven't done it.
And we have also another test in physics.
So you have
Third test. Not this week, but next week.
Robert should be next.
Okay. Just email me to remind me tonight. But email me today because otherwise it might be too late. Alright. Busy people. Okay. The papers actually are from last week. There's nothing new. They are the new files. So, where do we start? Let's look at the Cartesian coordinates. I think we did, from exercise 1, we did B and C. We did B and C. Should we do 1A? Should we simply finish off whatever we have left? Yes. Probably, yes, alright. So from exercise 1, we did B and C. And we can do 1A. So let's start with the simpler exercises, why not? That's a warm-up. That will be useful. And so, we simply have an integral from 0 to 1 by dx integrating x squared cube root of x f of xy dy. So we have an iterated integral. Remember that these are called iterated integrals because it's an integral taken repeatedly but by different variables. If you integrate several times by the same variable, it's called repeated integral. But this is called iterated because we are taking it by different variables each time. So the thing is that the way you write the iterated integral defines the order of integration. And therefore, we always start integrating by the integral that's actually visible clearly as a complete integral in one piece. In this case, I can see a complete integral by y. So this is how I would integrate if I knew what the function was. I don't know. Because I don't know, I'm not going to integrate. I'm only going to investigate this integral to see what this means, to see what it looks like, to see what we can do. And so, this integral, there are two curves defining it. Y equals x squared, that's the first one, as we see from this. So, y is x squared. And this is the cube, y is the cube root of x. The cube root function looks something like this. The cube root function looks something like this. Obviously, the graphs, so y is the cube root of x. The two graphs intersect, obviously, at the point 1, 1. So the region of integration is this, between the two graphs. Yes, x changes from 0 to 1. And so my integral, as written like this, starts integrated by the variable y, which means it starts going in the y direction. Integrating by y means we go in the direction of the y-axis. That's hopefully easy to remember. So this integral, as written, goes from x squared to cube root of x. So for every x value, it goes like this, integrating along the y direction, from x squared, see, there, to the cube root of x to this point, so up to there. And then when we have integrated this and this and this and this and this and this, we add these all up. So we integrate, afterwards we integrate by x, by dx, and of course we move through x values from 0 to 1. Now, to exchange the orders, to change the order of integration, I obviously would need integral by dy integrating the same function, which I don't know what it is, by dx. Which means I obviously need to change the boundaries of integration. So for this dx, I need to go in the x direction. If I integrate by x, I go along the x-axis. And in that case, you see, the boundaries would change. We start from this line, this curve, and end on that curve. So we start from the second curve, from what was the second curve in the first case. Now, if we go like this, we start from this curve and end at this curve. By the way, if I integrate by x, the boundaries of this integral have to be expressed in terms of y, because I need to obtain an expression in terms of y so that I can integrate it by y. And that's why, so if you see dy here, then the boundaries are either numbers or they have to contain x, because I have to make an x expression to integrate by x. In this case, I need to make a y expression to put there to integrate by y, and therefore I need to express the boundaries in terms of y. In other words, for this integral I can write x is y cubed. I do not exactly write the inverse function, but I do turn it inside out. I don't exchange the variables, but I simply turn it inside out. And for this function, obviously, x is the square root of y. By the way, it's the positive root because we are working in the first quadrant. It's the positive root. So, remembering that, going in the x direction like this, we start from this curve, the lower boundary should be y cubed. So, it's y cubed, and the upper boundary will be square root of y. Okay, I believe that in the answers I had what? X somewhere instead of y. I had mistakenly written x instead of y here or something like that. My mistake. When you have to understand, when I do those solutions, I do them very quickly and I never check them. So I do make mistakes. Alright. And dy, now again we see dy, y changes from 0 to 1. So the outer integral always have constant boundaries because there's no new variables. There's nowhere to get any new variable to express this integral. So these are always constants. The outer integral boundaries are always constants. The inner integral boundaries should be expressed in terms of the outer variable, but sometimes they might be constants. It happens. If the region of integration is a rectangle, for example, or if one of the boundaries is a straight line, a horizontal line, or a vertical line, they could be constant, or one of them could be constant. But basically, so we know that we have to start integration from that integral that we see completely as a real complete integral, complete starting with integral sign ending with dx or dy. Secondly, we have to remember that the boundaries of that first integral have to be expressed in terms of the other variable. And thirdly, if we integrate by this variable, and express the boundaries in terms of the other variable. This also determines the direction in which we go first. So the movement, in this case the movement was vertical along the y-axis. If we exchange the order, if we exchange the variables, then we have to go horizontally. We generally always go from the lower boundary to the upper boundary, but sometimes in a given integral, sometimes it might be turned upside down. If it's given, then you have to solve it as given. In this case, the change of boundaries, the change of variables looks like this. We cannot finish this because we don't know the function f. So this exercise was simply about sketching the boundaries, deciding, discovering or saying the region of integration, and rewriting the integral so that we can exchange the variables to do it in the other order. The reason why we want sometimes to do it in this order or that order might depend on, sometimes on the region of integration. It looks nicer going this way than going that way, for example. And sometimes, if it doesn't really matter, as in this case, not too much difference, it might make a difference depending on the function. Some functions might look nicer when changed afterwards, when integrated and the boundaries of integration are inserted. Some functions might look nicer this way and some other functions might look nicer that way. So that's not always easy to decide from the beginning. Now, from the second one, I think from exercise 2, we did 2D, definitely. We did 2D. Yes, last time, but I don't remember. Was that all? I think it was all. Yes, because the ABC integrals were actually quite nice. So it's good that we can start, or that we can go on today with easier, simpler tasks. 2A. So if we have xy, so remember that what this means. So we have pairs xy's of two numbers, coordinates of the point. From the real number plane, R squared is the real number plane, for which x is between 0 and 1, and y is between 0 and 2. So this is obviously a rectangle described like this. So all points from the real number plane for which x is between 0 and 1 and y is between 0 and 2. So looks like this. Looks like this. This is the region of integration. And evaluate the integrals. Okay, it doesn't say which way, in which order we should do this. So we may choose. And traditionally we start by y. So dx, x changes from 0 to 1, x goes from 0 to 1, y goes from 0 to 2, and the function 1 plus x plus y. dy this time. So I have rewritten the given integral into this form. Now what we did was, we look at whatever integral we can see completely, which one looks like a real actual integral and not something cut short. And we start with this. So sometimes, quite often, it's quite advisable to do it somewhere on the side so that you don't get too confused in the basic area of your work. Go to the side of the page somewhere and do it somewhere separately. So in this case, integral from 0 to 2, 1 plus x plus y dy, we integrate by y. 1 is a constant, integrating a constant, 1, we get just y. X is a constant. Integrate x by y. You'll get xy. Y is the variable by which we integrate. So the third component, y squared over 2. And now we see that y from 0 to 2, we have 2 plus 2x plus 2 again, minus everything is 0 for y. So what we see is 4 plus 2x or 2x plus 4, which is the expression we now have to integrate by dx. Now this, we found this green integral, this green framed part. We found it here. And now all we have to do is put it in there back, put it back in there and integrate. So it's from 0 to 1, 4 plus 2x by dx. Because this is basically a product, dx times a function. It doesn't matter that we have it here in the end after the x. After we have simplified that integral, we can put it before dx, because we consider this a product, dx times that integral. Now it's easy. 4x plus x squared between 0 and 1, so it's 4 plus 1 minus 0 is 5. The value of this integral. So you see, sometimes you get quite simple integrals. And yes, of course, in the test I will give you simple integrals to integrate on a rectangle, but not all of them. B is exactly the same boundaries of integration. The one thing that's different is the integrand, the function. So we can write, if we look at 2b, compare it to 2a, the region of integration, compare the region of integration, it's exactly the same. It's exactly the same. So I can do the same boundaries of integration because the region is exactly the same. So the boundaries of integration only define the region. The value of the integral is also determined, of course, by the function. So the region of integration and the function, they both work together. It's never been previous time. We've done it. This one. 2b, we did? Yes. Really? Okay. 2c? No. Okay, then let's do 2c. Okay. Those who missed 2b last time, ask your colleague. She has it. I had it, but obviously I erased it. Well, a week ago. Okay. Now the next region, let's start by looking at the region, is bounded by y equals 2x. That's a straight line. Y equals 2x is a straight line. Y equals 0, that's the x-axis. And x equals 1, that's the vertical line. X equals 1. And this is y equals 0, that's the x-axis. And now if I have the region bounded by these three lines, by the line y is 2x, by the line y is 0, by the line x is 1, then the region of integration is this triangle. It doesn't matter in which order we integrate here. Obviously one of the boundaries will be the line. And the other boundaries, the other three boundaries will be numbers from 0 to 1 and from 0 to line. Or maybe from line to 1 and from 0 to 2. We have to notice the coordinates of the intersections. So traditionally, as always, I'm used going by y first. So dx is left for later, and we start by this. The function 2x plus y, integrated by dy. So the y, okay, I went by dx for some reason. I do in the x direction, but I'm going by y. I wrote y, so I have to go in y direction. My mistake. Y changes from, obviously, from 0 to this line, which is 2x. And then, when we have integrated this, we see that x goes from 0 to 1. Or, you could do it the other way around. You could go by x first. So, 2x plus y, going by x, first of all, okay, I'll use the red marker to show this. So the x changes from, this is the entry point. This is where we enter the region and this is where we exit. So we go like this, in this direction. We start from this line, but remember, if we integrate by x first, these boundaries have to be expressed in terms of y, not x. Therefore, I need to write x is 1/2 y. I take the same equation, I simply turn it inside out. Express x in terms of y, not y in terms of x. And of course, this is the lower bound because we start here. So I start by 1/2 y and end at x equal to 1. So it can be a constant. And y changes from 0 to 2. The total change of y. Like this. So these two integrals should give you exactly the same value, exactly the same final answer. Whether they do depends on how correctly you integrate. Okay, so I think I want to start with this. Well, I don't want to do it like with this actually, by this integral, because it has this half.
Yes.
I prefer integers. Whole numbers are much nicer, so I will do it this way. But if in case sometimes you just happen to do it in the not quite the convenient way, unless you make a mistake, I'm accepting it. It doesn't matter, it's your choice. It's your choice. Okay, I integrate from 0 to 2x. 2x plus y integrated by dy. 2x integrated by y is 2xy. Y integrated y squared over 2. 0 to 2x. So now I put 2x instead of y because we are integrating by y. It's the y variable. So sometimes it might get confusing, so you have to pay attention. If your expression, the integral, contains both variables, both x and y, remind yourself, go back and look by which variable you are integrating, because that's the one for which these boundaries work. It's simply a place where it's very easy to get confused. Just a friendly warning. So make sure you put these boundaries into the correct variable. That's all. It's not so bad. So 2x instead of y gives us 4x squared. 2x instead of y, 4x squared divided by 2, that's 2x squared. Minus 0, 0 instead of y will give you 0. So it's actually 6x squared in there. Now I have to integrate it by x. From 0 to 1, 6x squared dx. The integral is 6x cubed divided by 3, it's 2x cubed. So we have to. If you do it the other way around, you should get the same answer. Okay. Now exercise 3. Okay, we did 2038, right? 20 come to 38. We did that last time, so I'm not redoing it. Again, there seems to be an error in the answer file, but the answer I had on the board last time, which was minus 11.2, is the correct one. So the answer I had for 2038, it was the correct answer on the board. The correct answer for exercise 3, integral 2038 was the correct one.
Minus.
We did 38, we did on the board last time, yes. Well, last week.
Minus 112.
The answer was minus 22.
No,
Minus 22.
minus 112. Minus 112.
Minus 11.2, yeah.
Yes, minus.
I remember minus 11.2. I remember minus 3.2, 32 over 10
Yes.
and 8. I remember that very clearly.
Yes.
And that's the correct answer. In the answer file I sent you, there's an error. Okay, so now we have from 1 to 2 dx integral from 3 to 4. So this is on a rectangle. No worries about confusing expressions. And now we have dy over x minus y squared. So yes, now how do we integrate this? This is a simple integral. This is a simple integral. But the problem, of course, is that it's confusing with the two variables. So actually what it looks pretty much like the integral dy, for example, 5 minus y squared. It's just x instead of 5, for instance. X is playing the role of a constant. X is playing the role of a constant. So, alright, I will write the correct thing in there, x, and it's from 3 to 4. So this is actually x minus y to the power minus 2 by dy. Which means I have to integrate this now. Minus 2 becomes a new exponent, minus 1, we add 1. When we integrate, we add 1 to the exponent. I know that so far you have had integration, you have had differentiation. When do we add, when do we subtract 1? Has become a little bit confusing by this moment, I know. Too much information for your poor brain. It happens, that's normal. Happens to me too. It happens to me too, don't worry. So it's x minus y to the power minus 1 divided by the new exponent times. Now there's one more thing. Not times but divided by. If I have minus y, remember I still have to divide by the coefficient of y. I still have to divide by another minus 1. Because we had this rule, f of kx plus b dx is the primitive function but divided by k. It's the same old rule for integration. Because it's not pure y squared derived. It's a linear function. If we have a linear function and integrate a composite function whose inner function is linear, then you have to divide by the coefficient of x. And the coefficient at the variable by which we integrate at this point is minus 1. Therefore, I need to divide again by minus 1. Normally, I would simply divide by minus 1 because of this. But because it's minus 1, not plus 1, I have to divide by minus 1 again. From 3 to 4. So what I have here is, this becomes a plus, so I have 1 over x minus y. from 3 to 4. Now, we integrated by y, so I keep going back and reminding you. At this point, it's always useful not to do things mechanically, but go back, check the variable, and remember that I have to put these numbers instead of y. So, instead of y. So this becomes 1 over x minus 4 minus 1 over x minus 3. Because I have to put the boundaries of integration into the variable by which we integrate. If you see more than one variable, now imagine what triple integrals would be like.
Yeah.
The triple integrals are pretty much like this, but a little bit more horrible, or much more horrible, because then you have to think about expressing the boundaries of the inner integral in terms of two other variables. So they are a little bit horrible. Okay, so now we can, from 1 to 2, now this is integrated already, and it's that. So I can write 1 over x minus 4 minus 1 over x minus 3 by dx. Now, I do remember that these were the logarithms when we integrated. So it's ln x minus 4 absolute value minus ln x minus 3 absolute value from 1 to 2. And so that I don't have something too complicated, remembering the laws of logarithms, I can write these two logarithms as a single one. ln x minus 4 divided by x minus 3. Remember, if we subtract two logarithms to the same base, we can divide the expressions inside the logarithms. That was one of the logarithm laws. So if I had log of a minus log of b, we can write it as log a over b, of course, using the same base. And if it's plus, then we can multiply them. Simply because it's easier to apply the constants now. So now it's ln of minus 2 over minus 1. So it's actually ln of 2 minus ln of, now I put 1 in there. So I get minus 3 over minus 2. So it's 1.5 or 3 halves. Or I can write the same law again, once again, because again I have the difference of two logarithms. So it will be 2 divided by 3 halves, which means ln of 4 over 3. Well, that's obviously all. Nothing much to do. Nothing much to do here. If you need the exact or the approximate value, then you can use your calculators. I don't care for the approximate values. I'm a theoretical mathematician. I'm not an engineer, so I don't particularly like approximations. I like exact values. Okay. And the third one. Integral from 0 to 2 by dx. Integral, okay, minus 4 plus x squared. And for minus x squared, it's the exact opposite. Alright. The function is nothing. The function is nothing. So actually, if you have something like this, without any constants in there, without anything, this will actually give you the area of the region of integration. If there's nothing else in there, it simply gives you the area, that's all. Alright. So integral of dy by whatever is simply y, because it's 1. The integral of 1 is simply y from, obviously, minus 4 plus x squared, 4 minus x squared. So we put these into y. Now it's easy, no confusion at all. So 4 minus x squared minus 4 plus x squared, which means I have 8 minus 2x squared now. And now this is what I have to integrate there. Put it back there. From 0 to 2, 8 minus 2x squared dx. So you see, it's actually risky to put more complicated expressions there because it might become complicated too fast if the boundaries are not straight lines. So 8x minus 2x cubed over 3, 0 to 16 minus 16 over 3 is something. 5 1/3, so it's 10 2/3. All right. Now we should move on to the polar coordinates. Now let's have a look at 4. So 4D, you cannot do it at the moment. I actually wrote down the number of the question in the book, and I will look up because in D, I think I have forgotten to write down some boundaries. There are not enough boundaries, so you cannot do 4D at the moment. I will look up the exact exercise, and I will try to add boundaries to it, and perhaps send them to you or something. And then obviously I have to improve my answer file. Did we do anything from 4? A or B
Yes,
or C?
C.
We did C.
Yeah.
Very nice. So we should do A, B. And we cannot do
D.
D at the moment. No way. Alright. So the boundaries of integration. X is between 0 and 1. Y is also between 0 and 1. So we can actually write the boundaries of integration at once because they are very, very simple. We see that X is from 0 to 1 and Y is from 0 to 1. But the function is not very nice on one hand. On the other hand, it is quite nice because if we remember that x squared is a constant, then we have the arctangent. The integral resulting in arctangent. So, alright, integral from 0 to 1, x squared dy over 1 plus y squared. We can actually take x squared outside the integral because it's simply a constant for this. It's nothing for this. So basically what we see is we can take expressions containing only x out of this integral, the factors containing only x, can be taken outside of this integral because they are just constants. They don't contribute anything to the integral in terms of y. So I could take this x squared and write it there into the x integral because I don't really need it here. But okay, I left it outside, I took it outside. So in this case, dy 1 plus y squared, which means it's x squared times arctangent of y, the classical integral from the list. X squared. Now, arctangent of 1. What is the angle for which the tangent is 1? Pi over 4. 45 degrees, it's pi 4. Arctangent of 0. For what angle the tangent equals 0? 0. Okay, so we see that this integral will be pi over 4 x squared dx. Okay, that's not a problem. I don't even need to bring pi over 4 outside. I can integrate it at once. So it's pi x cubed over 12 from 0 to 1, which means it's pi over 12. So this is, it looked bad at the beginning, but it turned out to be quite simple. It's a basic integral. But as I said, it's not a rule. It's not a rule that double integrals always look bad and are simple, and it's not a rule that they always look simple and are actually bad. It happens. So, because they are double integrals, intuitively it's quite often difficult to tell whether it's going to be difficult or hard to do or easy to do. The triple integrals are the worst. Alright, now B. We still have B, and that's the last one for this paper. Again, the boundaries of integration are quite simple, and yes, let's start by y. Why do I prefer to start integration by y? Because the integrand, the function, contains quite a lot of x, but y is only in one place. So that's easier to integrate by y first.
So boundary.
I think. So dx from 0 to 2.
No.
No.
So minus
Sorry.
1.
Where am I looking? I'm looking there. Yes, x from 0 to 1. Sorry.
0 to 1.
X from 0 to 1. Y goes from minus 1 to 0. The function is x times e to the power xy. We integrate by y first. Okay. In this case, I will actually push x out of this integral because it's just a constant for it. So it is acceptable. Yes, you can do it because this is a product and this is a constant for this integral. So if it's a factor, I just put it out. So we have e to the power xy dy. So now, okay, minus 1, 0, e to the power xy integrated by dy. It will be xt, yes. It will be integration by parts. Okay, painful moments. Okay, integrating the exponential function, you basically get the same exponential function, but you have to divide by the constant x. Again, the same rule. It's like integrating e to the power 3x. You get e to the power 3x divided by 3. Minus 1, 0. We put it in y. So if y is 0, e to the 0 power is 1. So 1 over x. Minus, now we put minus 1 instead of y. We get e to the power minus x over x, or rather, we get 1 over x e to the power x. Doesn't look nice. No, nothing too pretty. Just don't make too many signatures there.
If we had the x, they would also go away, or no?
No, we go there. Yes, the x will cancel these out. That's actually good. So now what we have, putting it back, x times 1 over x minus 1. Okay, it's easier to leave it in this form because it will be easier to integrate. As I said, it's not always immediately predictable. So it seems that this form is still better than this with the minus and all. So e to the power minus x over x dx. Now we can see that this x will cancel these out by multiplication. So we get 1 minus e to the power minus x dx. And see, it's not so bad. So it's x plus e to the power minus x. Remember that minus will change the sign in front. 0, 1. Fortunately, no integration by parts. So it's 1 plus 1 over e minus 0 plus e to the power 0 is 1. So actually 1 and 1 cancel out, so I simply get 1 over e. Final answer, simply 1 over e. So now we have to go back to the polar coordinates. So for the polar coordinates, I would like to give you some hints for polar coordinates. Just a few hints, they are not in the paper, but still they are useful. So let's remember that for transforming into polar coordinates, we can write x equal to r cosine phi, y equals to r sine phi, sine phi, and obviously x squared plus y squared is r squared, because r is the distance of that point from the center, from the origin of the coordinates. And yes, of course, the integral itself of xy, the integral itself is changed into an integral f in terms r phi r d phi dr. So the thing is that we get an extra factor r. That's the important part to remember. Of course, we use these formulas to change the function into the polar form. We use the same formulas and some graphing to decide the equations for the boundaries of the region in the polar form. The same region, but it's simply expressed by r and phi. But the important part is this, that we do get an extra r. We do get an extra r when we transform into polar coordinates. So for the integration, some useful tips. For instance, it could be that the region of integration is actually some region going around the center, the origin of the coordinates, or the pole. The region of integration is situated like this. In that case, we of course integrate from 0 to 2 pi, so 0, and we go, the angle changes. From 0 we go full circle for the angle, right? So from 0 to 2 pi, that's d phi. And then we integrate, the inner integral goes integration by r, so f r phi r dr. But from 0, because the radius, the distance changes from 0, from the pole to the boundary. If this is the boundary r of phi, some function r, the function of r depending on phi. So what we have to do is this. We simply integrate the r from 0 to the boundary. Of course, we have to figure out the equation for the curve. And then we understand that we go the full circle in this situation. So if you see a situation where the pole or the origin of coordinates is inside the region of integration, you can go like this. Of course, sometimes
The boundary is 5, right? It's a 5. First boundary. Second boundary.
2 pi.
5.
It's 2 pi. Better? Okay. 2 pi. Because it goes full circle from 0 to 2 pi. Of course, you can do from minus pi to pi, it would be the same, but it depends on, well, 0 is always nicer to use. Although sometimes pi and minus pi are nice enough. So this is the first situation. Another typical situation is, it seldom happens though, but it's sometimes it's useful. For instance, we have the domain passing, the boundary of the domain passes through the origin or the pole. Here is the polar axis, and actually we can find the tangent line at that point. We can find the tangent line at that point. So then, obviously, we have some angle alpha there, and this angle is obviously alpha plus pi. So we can still integrate from 0 to this boundary line. So this would be still the same, from 0 to the boundary line to the curve r depending on phi, but the phi angle will be from alpha, because this is the tangent line, from alpha, from this to alpha plus pi. That doesn't happen too often, but sometimes it does. For example, when you have a circle passing through the origin, as we have sometimes, we have the circle with the center on the x-axis, for example, a circle like this. So we can integrate from minus pi half to plus pi half. It depends on that tangent, on the slope of that tangent. So this is possible and mostly used for circles that pass through the origin. If this is actually a circle passing through the origin somehow, then this is quite useful to notice. Simply to, let's say, understand, decode, decipher the boundaries of integration. Now the third term, sometimes you can see the boundary of integration is, well, something like this. You can see the tangent lines to whatever it is, or something like this. Okay? So if you see the angle alpha and the angle, for example, beta, you can integrate again from 0 to this curve, again from 0 to r phi, the same, but the angles, the boundaries for the outer integral will be from alpha to beta. This to this. We see that quite often. We see this situation quite often. And again from 0 to whatever equation there is. Finally, we might have a situation where the region of integration is completely away from the origin. Well, obviously, I left it for the last one because the worst. So if we have the region of integration quite away from the pole, from the origin, then obviously we should find the tangent lines. Sometimes they are given. We should split the boundary of this region into two parts. So this would be R2, some function, and this would be R1 depending on phi. So we have one angle, we have the other angle for the tangent lines, and then the R would go from R1 to R2. Not from 0 to the boundary line, but from the first boundary line to the second boundary line. So this is the third typical situation. So d phi, and this will go from R1 expressed in terms of phi, of course, to R2 expressed in terms of phi. The function mechanically, without thinking, because it's simply formally, I'm simply writing this formally. Of course, it depends on your function, whatever you have in there. So there are, let's say, in order of complexity, 4 typical situations. Sometimes, of course, you have to split the region of integration into more parts, and for each part use perhaps a specific type. But these are basically the 4 specific types that might help you deal with these integrals. All right. Now let's have a look. At our exercises, because last time we really didn't have too much time. And as I said, it's more important to practice here than to rush on with the new material. So I don't think we did anything last time. It's painful. All right. Let's start by exercise 1. Integral y over square root of x squared plus y squared dx dy. The region is given by x squared plus y squared less than or equal to 1, and x squared plus y squared less than or equal to 2y. We had something similar. And I will repeat the explanation. So this, obviously the inside of a circle, obviously the circle has the center at the origin, at the pole of the coordinates, and obviously the radius is 1. So the circle x squared plus y squared equals 1 means simply radius squared is 1, or rather means the radius is 1. That r variable equals 1. But it's still the same circle. It's the circle, center at the origin, radius 1. It goes like this. It's still the same circle. It's only written this way. It's much simpler. R equals 1. It's much simpler than this equation. So this is one reason why we do a lot of integration in polar coordinates. This makes it easier. The second one though, x squared plus y squared, I will bring minus 2y to the left equals 0. Now I would like to remind you that in general the Cartesian equation of a circle x minus x0 squared plus y minus y0 squared equals r squared means that the center of this circle is at this point. So for example, if the center is at the point 3, 4, I would write x minus 3 squared plus y minus 4 squared equals whatever radius squared. So I look at this and I see that I can change that equation into this form. I simply need to complete a square. Obviously, it will contain y. There's nothing with x, so x squared will remain as it is. So what I'm going to do is add 1 to both sides, which makes this a complete perfect square. X squared plus y minus 1 squared is 1. Now I know that this is a circle with the center at 0, 1, which is there. No, 0, 1 is this one. This is 0, 1 on the y-axis. I also know that the radius is 1. So it will pass through the origin and the point 2 on the y-axis. So the circle will go like this. Okay, not very pretty, but hope you get the idea. Alright, so the region of integration is this. Inside of the two circles. And now, how do I integrate it? Well, obviously, if I connect these 2 points, you see there's this segment of a circle and then there's this segment of a circle. If I connect them with a straight line, I get those segments split off. And then I see three separate regions of integration. I see one region of integration is this one. Notice that this is the tangent line of that circle, the upper circle. The x-axis is the tangent line. So basically, we see that from 0 to this angle, we have to integrate from 0 to this circle. I haven't expressed it in terms of r and phi yet. But then, here from this angle to pi, I have to integrate again from 0 to the equation of this circle. But between these two poles, between these two segments, in this part, I have to integrate angle this to angle this, but r goes from 0 to this circle. So we have three parts, three separate integrals. Let's have a look at the angles and the equations of these. So if I want to write this in terms of r and phi, in terms of polar coordinates, the equation for this is r equals 1, as we already saw. This is already there. So the equation for this, we take the original form, and we have r squared equals 2r sine phi. Remember that the y variable transforms into r times sine phi, and I have this. So that means r equals 2 sine phi. So the equation of this circle is again surprisingly simple. R equals 2 sine phi is the equation of this, of the circle in red. The circle, the red one, has the equation this. The green circle has the equation this. And so this integral will consist of three parts. There's another thing. We need angles. We need the phi values for integration. So let's remember that these two circles have exactly the same radius, they are the same size, and each of them passes through the center of the other circle. What does it tell you about the angles? This is the radius, this is the radius, this is the radius, this is the radius, this is the radius. What does this mean? So all these four segments are equal to 1, the length, because it's the same radius. This means that all the angles in these triangles are 60 degrees, which means if this is 60 degrees, then this is 30 degrees. This angle is 30 degrees, which is pi over 6. And this, obviously, the angle from 0 to this line, or this ray, this half line, corresponds to the angle 5 pi over 6, the symmetrical one. And this, of course, corresponds to pi, the horizontal tangent, and this corresponds to 0. Angle 0, angle pi over 6, angle 5 pi over 6, angle pi in radius. So now we can write this. Oh no, I still have the function. You see how much work it is? It's a lot of work.
Time is up.
The time is up. Okay. I will only write the integral, I will not calculate it. I want to finish writing it. So it's, if y is r sine phi divided by r, so I actually have sine of phi times r divided by r times another r, like this. So I have part it will be from 0 to pi over 6. It's this part, the red part. And the radius will go from 0 to 2 sine phi. From 0 to 2 sine phi. I'm not doing anything more for that. The second part will go from pi over 6 to 5 pi over 6. And the integration will be from 0 to the green circle, so from 0 to 1. 0 to 1, integrating the same function by r. And the third part will be, guess what? Like this, only the angle will be from 5 pi over 6 to pi. So the third part, and then finishing. Don't worry, I want to end this too. No less than you. My fondest wish. From 0 to the red one, so 2 sine phi r dr. Okay. So this is the first, this is the green one, and this is the second red one. And when you add these up, you get your answer. Lots of work. Yes. I have a sneaky suspicion that on Thursday we still need to finish this before we move on, because that's more important. You always can read up if necessary on what can be accomplished using